In this video, we're going to prove that the discrete metric on a set is truly a metric. So what's that look like? And just to remind you, what's a metric? We want to try to generalize the notion of what a distance is. And what you're probably used to is, I think, the distance between two real numbers, right? If you're on a number line, if I want to talk about what's the distance between two real numbers, I just count how many units are between them. So in other words, if that's A and that's B, the absolute value of the difference is what the distance is. What we want to do is we want to generalize that notion of distance so that it applies to any set. So like, what if I didn't have the real numbers, say? What if I just had a set with some letters like A, B, and C? How do I put a distance on that set? What are the properties of a function that allows me to call it a distance function? And so again, that's a metric. But anyway, so here is our general setup. X is just any set. And so we're going to define this function from x cross x, that's the Cartesian product, to the real numbers. Remember, that's always what a metric's going to be look like. You plug in two numbers into the metric and it spits out a real number is what it says. So what's the formula for this d? What's it do? So d applied to x comma x should be 0. So in other words, the distance from x to itself should be 0, is how you should think about that. Otherwise, the distance from x to anybody else is 1, as long as it's truly anybody else, right? As long as your two inputs are not the same thing. So, in other words, I just get this piecewise function that's either 0 or 1. The only time it's 0 is just saying that the distance from a point to itself should be 0. Otherwise, the distance is always going to be 1. And what we want to show again is that this satisfies the criteria to be a metric. And what we'll do is we'll go through and remind you like what is the criteria to be a metric, and we'll just verify piece by piece how come this formula allows me to do that. So let's do that. So I got to get rid of some of this stuff here. I didn't think about that when I was erasing, but give me a sec. Cool. All right, so D is a metric if it satisfies each of the following. So number one, we need to make sure that the distance from any point to another point is always non-negative. So what do we have here? Let's look at our formula. Well, this distance function's kind of nice because it says, look, your distance is either 0 or 1. It's got to be one of those two numbers. So of course this is satisfied. So definitely distance is at least 0. So we'll put a little check mark by it in green, making sure we're done. So that's the first property of being a metric. The next property to verify to make sure that D is a metric is when is the distance from a point to another point equal to 0? That happens exactly when, if and only if, x is equal to y. All right, so you've got an if and only if, so you've got a biconditional. And let's do the forward direction. Let's do this. Maybe I'm thinking about that as, well, if the distance from a point to another point is 0, we want to conclude that x is equal to y. What we're actually going to do to prove that direction is the contrapositive. Remember, we're going to assume not q here implies not p here. So notice we're starting with, what if x is not equal to y? Well, let's take a look. What's our distance function do? Well, if x is not equal to y, the distance is 1 between x and y. And so in that case, just like we just said, the distance from x to y is 1, which is certainly not equal to 0. So we just came up with not p. So we just showed not q implies not p, which is the same thing as p implies q. So that's the contrapositive. Now let's go the other direction for this if and only if again. Now we're actually going to show if x equals y, then show that the distance from x to y is 0. And well, if x is equal to y, the distance from x to y, why don't we just replace this y by that x, right? This says it's legit to do that. And of course, we know that that's equal to 0, right? Because again, the definition of our metric, the distance from x to itself should be 0. So there we have it. So we conclude p at the very end. So that's how we get p. So that is the second property of being a metric. Put a little green check mark that we're done with it. The third property is sort of some kind of symmetric property that a metric should enjoy, like the distance from x to y better be the same thing as the distance from y to x. And in this case, well, if x is equal to y, then when I write this out, I could just swap the x's for the y's so that I get dxx equals dxx. So of course that's true. And in the case that x is not equal to y, maybe in that case we'll actually apply the definition of our metric here. The distance from x to y, if they're not the same input, is 1. Right? And again, I'm referring to the definition of the discrete metric here. But in that case, what if I just switch these around? Well, y is still not the same thing as x. So again, by that definition, the distance between y to x is also 1. And so what's the point? You get the same thing. Therefore, dxy and dyx are the same. The last thing to check is the triangle inequality. So I need to make sure that the distance from x to z is always less than or equal to the distance from x to y plus the distance from y to z. That needs to always happen. And the way that I'm going to do this is just by some cases here based on how x, y, and z might relate to each other. So the first case, what if they're all equal? And then I'm going to think about, well, what would each of these expressions here look like if they're all equal? Well, if they're all equal, each of these would have to be 0, right? Because I know the distance from a point to itself should always be 0 as far as the discrete metrics is concerned, and really any metric is concerned. Anyway though, so 0 less than or equal to 0, again, I just want to emphasize that I'm taking these zeros. Where is this inequality coming from? I'm literally just thinking about evaluating each of these expressions, in this case that x, y, and z are all the same thing. So I get something that's true, therefore the inequality holds for case 1 here. Case 2, what if x is the same thing as y, but neither of those guys is the same thing as z? In that case, again, thinking about these expressions up here, well, if x is not equal to z, then that's 1. And if x is equal to y, then that's 0. And finally, if y is not z, then that's 1. So that inequality looks like 1 is really less than or equal to 1, which of course is true. Case 3, what if I switch a few around? What if x is not the same thing as y, but y and z are the same thing? In that case then, again thinking about this, x is not the same thing as z is what I'm trying to say. So that this will be the 1 on that side. And x is not the same thing as y, so this should be that 1. And but y is the same as z, so that should be 0. Nonetheless though, I get an expression 1 is less than or equal to 1 plus 0 is certainly true. The last case I need to consider is what if all 3 of my points are distinct? In that case then, each one of these expressions up here evaluates to 1. And so it's true that 1 is less than or equal to 1 plus 1. So that's true as well. And there you have it. We verified the 4 kind of axioms of what a metric are and the definition of a metric. Since they're all true, that shows that the discrete metric is certainly a metric on any set that you put the discrete metric on.